Our next speaker is David Sherret, and he's passionate about healthcare, and he works as a developer at Synaptive Medical, where his products are used just up the road at the Swedish Neuroscience Institute. So please help me, join me in welcoming David Sherret to the stage.
Hello, everyone. Again, my name is David Sherret. I'm from Toronto. This talk is on static analysis and source code manipulation in TypeScript. So writing code that analyzes code bases, programmatically manipulates them, and generates code. So first we're going to talk about abstract syntax trees. What are they? How are they useful? Then at static analysis. Third, code manipulation. And finally, we'll look at some use cases. Before we begin, I want to emphasize that almost everything I'm going to say in this talk can also be applied to JavaScript code, since we all know TypeScript is a superset of JavaScript. So let's jump into it. Here's our first task of the talk. We want to generate a report that prints the names of all the class declarations with an extends expression. So what do I mean by that? Well, here's an example of some declarations. And we're looking for the ones that look like this. Okay. We also want to print the ones that are nested within other declarations like namespaces and functions. But for this example, we don't want to print class expression names. We don't want to deal with class expressions. So how could we solve this? Let's look at this example file. A beginner might think they could easily solve this by using regular expressions or by building a simple parser that first looked for the class keyword, then some white space, then a string that matches an identifier, then some more white space, and finally an extends keyword. This should work, right? Well, not really. What happens if the code looks like this? Or like this? Or for some strange reason, like this. This is syntactically correct TypeScript code, by the way. So when we're dealing with seemingly straightforward static analysis problems, we don't want to be dealing with disasters like that. What would be easier is if we took the text in the file, sent it through a parser, and produced an abstract syntax tree, or AST for short. Once we have an AST, solving our problem becomes trivial because it's very simple to write an algorithm that inspects one of these trees. Now, how do we get this AST so we can work with it? Well, there's a great implementation, and it exists within the TypeScript compiler. So currently, when you compile TypeScript code, say run this command, there's 4 main steps that happen. Parsing, binding, type checking, and emitting. The step we're interested in is parsing. So usually the internals of a compiler wouldn't be accessible for us to use individually, but lucky for us, the great people on the TypeScript team have created the TypeScript Compiler Api. This is an API we can access by importing like so. And on this imported TS object, there's lots of useful functions for us to use. For getting the AST from some text, it's easiest to use the create source file function. This function will use the parser to parse the provided text and return the root source file node of the AST. We could then navigate from this root node and visit other parts of the tree. Now I'm going to show you a visual representation of what one of these returned ASTs look like. This is a website I created, and it's available at tsastviewer.com. And it gives a visual interactive view of the AST that the TypeScript compiler creates. This was created specifically with TypeScript in mind, and is largely inspired by the AST viewer created by Bazarat that exists in Atom TypeScript. On the left here is the source file text. In the middle is the full AST, and on the right is the properties and some of the methods that you can get on the selected node. So in this case, the selected node is class declaration. It's kind of hard to see, but it doesn't matter too much. So this is the actual, this AST produced by the TypeScript compiler is much more detailed than the previous example I showed you. This is a zoomed-in view of the middle section that shows the AST. One part I want to highlight is that every node has a syntax kind, and this is showing them. For example, we can see the nodes in this tree have a syntax kind of source file, syntax list, class declaration, and so on. Anyway, I recommend going to the site and playing around with it. It's an excellent way to learn more about TypeScript's AST. Now that we understand a bit about the AST, we can now talk about static analysis. So for this demonstration, we're going to implement what we talked about earlier, which is to generate a report that prints the names of all the class declarations with an extends expression. Before we begin, I'm going to quickly show you the project we're going to be working with. This is a simple application with a bunch of TypeScript files. It doesn't really matter what this application does, it just, it has TypeScript files. Within it, we have a tsconfig.json in the root directory, and an src directory that contains the application code, and a scripts folder that contains the scripts we're going to write today. Most notably in here is note store and person store. Both of these have extends expressions. So to do our analysis, we could use the compiler API directly, but it would take a lot of time to explain it all, and it has a very steep learning curve. That's why instead I'm going to show you a library I've created for doing this. This library is called Simple Ast. It wraps the TypeScript Compiler API and gives you access to nodes, symbols, and types, as well as the program, language service, type checker, and emitter, among other things. One great feature is that you will always have the ability to fall back to the compiler API in case you need to. And for code manipulation, it edits the text directly based on the AST. This is done to make manipulations much easier and selective to the portion of the file being edited. And you can install it via npm. So let's get started. First, we need to import the default export from Simple Ast and instantiate it. Here I'm also specifying the path to the tsconfig.json relative from the root directory. This will load in all the compiler options and automatically populate this object with all the source files that relate to that tsconfig. So in this case, it would get all the TypeScript files in the specified root dir folder, which is src. If you don't want that behavior, you can disable it by setting the add files from tsconfig to false. Additionally, if we were analyzing a JavaScript project that didn't have a tsconfig.json file, we could instead set the allow.js compiler option to true, then use add existing source files to populate the project with source files based on a file glob. That would be another way to get going. But in this case, we're going to stick with specifying a tsconfig.json because that's easiest with TypeScript. Now that we've done our setup, here's the rest of the code that solves our problem. So we're looping over all the source files in the src directory using a file glob. Then we're looping over all the descendants of the source file that are class declarations. We're doing this using the get descendants of kind and providing a syntax kind of class declaration. You can see here that the syntax kind is a named export from the library and is an enum that contains our class declaration syntax kind, which is what we're looking for. Then for every class declaration, we want to check if it has an extends expression, and we can simply do that by checking the return value of the getExtends method to see if it's not undefined. Finally, if that's true, the source file path and class's name are logged to the console. Okay, so I'm just running a file I already have written, which is the code we just saw. And you can see it found our note store and person store class. If we were to remove this and run it again, it only finds our person store. Now we're going to look at a real example of static analysis. This is an example from the library itself. So within this library, you can not only get source files, but you can also get objects that represent directories. This method, getDirectory, will get the directory by the specified path or returned undefined if it doesn't exist. The annoyance with this is with strict null checks, we'd often find ourselves having to throw our own error if it's undefined or assert it as not undefined, and possibly one day when it's actually undefined, we'll get a non-explanatory null reference error somewhere in the code. So what would be better is if the library provided a corresponding or throw method. This would get the directory by the specified path or throw an explanatory error message when it doesn't exist. So that allows people to write not too much code. And so in my analysis scripts of the library, I wanted to write some source code that ensures a corresponding or throw method exists when a method possibly returns undefined. For this example, I'm going to start from the assumption that we already have a class declaration node, and that's called classDec here. On this class declaration, we'll loop over all the instance methods. And here's the code that solves it. Basically, we check if the return type is nullable, meaning null or undefined, and if it doesn't have a corresponding or throw method. If so, then log a message to the console about it. One point I want to highlight here is that the getReturnType method will internally use Typescript's type checker to get the return type. That's useful because from the AST alone, it's difficult to tell the return type for method declarations with an implicit return type. So you can see here for this getDirectory method, this code wouldn't log when getDirectory or throw exists, but it would log when it doesn't exist. Just a side note, there's better ways to write this, and it could be generalized to work with interfaces and static methods, but this is just a basic example. Okay, now we're getting to the good stuff. Using what we previously learned, we're going to go into the files of a code base and programmatically manipulate them. So imagine this, you're on a team and you've got thousands of files of code. One day you've got this crazy idea that you love snake case. Snake case is just so cool. You want to change the code, but you feel defeated when you realize it would take too much time. You've got better things to do. So you concede to live with the code as is. Well, traditionally that's pretty much been the case. But I'm going to show you how this isn't actually that much work to do, and we can make our snake case dreams come true. So we're going to do a programmatic refactor that changes some of the coding standards in the code. This example is going to be somewhat simplified. Our requirements are all class declaration names should be converted to snake case. And if the source file has an exported class declaration of the same name, then the source file name should be converted to snake case as well. So in this example, we're only going to deal with class declarations. But remember, there's more generic ways to solve this for functions, interfaces, and so on. Let's get started. The setup is similar to before. Again, we're going to loop over all the descendant class declarations. I've added a comment here that reminds us what we're doing. Next, I wrote a very simple function for taking a name and making it snake case. It takes a string and then converts it to snake case. The internals of this function don't matter. Just know the principle that it accepts a name and changes it to snake case. Now we'll take the class name and get it as snake case, and then use the rename method to rename the class. That rename method uses the Typescript Compiler API's language service to rename the class. So the functionality is equivalent to right-clicking on the class name in an IDE and clicking rename. So you get all that power here in a single method call. Next, we're wanting to rename the source file if it contains an exported class with the same name. First, we'll get the name of the file without its extension in snake case. Then we'll search for a class with the same name. Remember, the classes are in snake case now, so we need to search for them as such. Note that this getClassName method, this getClass method, will only check for class declarations of the source file and not for descendant class declarations. Then check if the class exists and is exported from the file. That's done on that if statement. And if that's true, move the source file to its new home as snake case. A neat point to note is that this isExported method will use the compiler symbols to figure out if it's exported. That means if the class declaration is exported via an export declaration on a different line, then this will correctly still be true. Unfortunately, I'm not going to have time to talk about symbols today, but I recommend you look into them. Okay, here is one last step we have to do, and that's save the project object. Everything that's done above doesn't hit the file system until you either call save or save sync on the main project object. It's transactional. Okay, let's run this. Okay, you can see a bunch of our files have been renamed. So all these identifiers have been renamed. The module specifiers have been changed automatically for us. And you can notice here this person wasn't changed, and that's because it's an interface. So it's gone through our entire file code base and changed everything. You can also see in here. This is another real example from the library, and it's on manipulating declaration files. So in the library, the getDescendants method returns the appropriate node type based on the syntax kind passed in. For example, passing in a class declaration syntax kind would mean the return type of this method is an array of class declarations. So that's really nice, but how does that work? Well, here's typically the method signature of a method like this, what it would look like. It accepts a member of the syntax kind enum, and then would return an array of the base class, which is node. And further, that means we'd have to do a type assertion to get the array of class declarations. That's a problem. I don't want people using the library to have to deal with doing these type assertions all over the place. Instead, it would be nice if, based on the passed-in literal value, the compiler had the information to show the appropriate return type. Well, this is a portion of my declaration file, and in it is the getDescendantsOfKind method. Now, to solve this, what could easily be done is to manually write an additional method overload that accepts a literal value of syntax kind.classDeclaration and returns an array of class declarations. But this is a lot of work. I would have to write about 150 method overloads, and I don't want to do that for, I just don't want to do that at all. And I would also have to do it for the getChildrenOfKind method. So 150 times all the methods that use it, it would be quite a lot of work. So what I did instead was wrote a script that analyzed the library to first figure out what nodes map to what syntax kind. From there, I had it analyze the declaration file for all methods that accept a syntax kind and return a node, possibly as an array. And finally, I manipulated the declaration file to add the specific method overloads, which is very simple to do. There's an insert methods method on class declaration. So that's only a small subset of the overloads that would automatically be added, and it would be done for all the methods that matched. So that's how I added that feature with very little maintenance overhead. It's a feature that maintains itself, and because of it, the users get a much better experience. So there might be a clever way of doing that with map types, but I'm not sure. Let me know if you know. There is? Okay. Yeah. Okay, so I need to do that in there, but but you get you get the basic idea of how you can do stuff like this. So what are the use cases for static analysis and source code manipulation? Well, there's a lot of potential use cases and many more waiting to be discovered. My view on this subject is that the easier this becomes to do, the more use cases will be thought of and implemented. So here are some use cases. Automated enforcement of application-specific rules. This would just be custom scripts that would allow you to check that your application is following certain rules you want to enforce. Next, automated enforcement of API conformance. An example of that would be the get directory or throw example I showed you. Then identifying API changes. This would be useful for checking libraries for additions, breaking changes, and for determining the next semantic versioning. It could also be used to automatically check that libraries are following semantic versioning, because people like to lie a lot. Next, programmatic refactors. Also something I've really wanted is finding errors in code and documentation. Identifying documentation gaps, so seeing what parts of an application aren't talked about in the documentation. Next, documentation generation from source code. This has actually been being done for certain things, but a great example of this is CompoDoc. That's developed by Vincent Ogloblinski, and it uses the compiler API and Simple Ast to automatically generate documentation for Angular applications. Next, metrics on code complexity, basically analyzing all the source files and giving each section of code a score or maybe highlighting problem areas. Next, source code transformations between versions of a library. I can only see this practically working within a company, but essentially you would release the library, have it go through all the other code, change it, and then maybe after it changes the code, it would automatically open up a code review. Another example of this is converting like Angular.js projects to Angular. I've been talking with a guy who's been internally doing this at his company and using Simple Ast, and he's had a lot of success doing it. Next, source code transformations between JavaScript and TypeScript. In the past few months, there's been some libraries released to do this, such as TypeWiz and React JavaScript to TypeScript transform. That's Mosen's library. Both these projects use the TypeScript Compiler API directly to achieve what they do. Here's a paper someone sent me that I wanted to highlight. I'm not going to discuss all the details here, but what's outlined in this paper could be applied to JavaScript and TypeScript. Finally, this is the last slide. Automatically generating client-side code from server-side code is another thing that we can do. Manipulating TypeScript declaration files. And finally, there's many more use cases waiting to be discovered. Anyway, that's my talk, and thanks for listening.